Okay, we have here on the board the sum from n equals 0 to infinity minus 1 to the n over n plus c. And I want to get a general formula for this. I found it pretty interesting. It's very similar to the alternating harmonic series. You notice, like if c was 0 and n was 1, and I think we have to have this be n plus 1, then you get the alternating harmonic series and its natural log of 2. This is kind of nice because it's going to be more general and cover some different scenarios where we're adding a constant onto it. So to get started with it, what I want to do is break it up into the odd and even terms. Now, you will notice on this thing right here, for the alternating harmonic series, we don't have absolute convergence. So we can't rearrange terms, but within the terms, we can break it up this way because for any one term, it's just a value that we can shuffle around as long as we don't add it to some other terms down the road a little bit. So doing things like breaking up the even and odd terms within a single term is going to be fine. So to do this, like n equal to 0, that's going to be even. You'll notice whenever n's even, you're just going to have a 1 in the numerator. And so to express the denominator so that we always have even terms, I'll write this as 2n plus c. And then in order to get all the odd terms, you notice when n is odd, it's always going to be a minus 1, so I'll have a minus in front. To get an odd term, I can write it as 2n plus 1 plus c. And then what I want to do in order to set this up, in order to use the Digamma function, is I want to plug something in here that's not going to change it. So what I can use, what I want to use here is going to be 1 over 2n plus 2 minus 1 over 2n plus 2. Doing it this way, I'm just adding 0. And I'm just choosing 2 on the coefficient to match this right here. So let me plug this into the middle of our sum and let's see what we have. So again, what I've done here, we just added a 0 into the middle of this. But now that we've got a 2 on all the n's, I can factor a 1/2 in front of this. And then let me reorder this. So let's take this one and bring it out front. But with the half factored out, this becomes 1 over n plus 1 minus, then this is going to become n. I'll group the c and the 1, so we can write it as plus c plus 1 over 2. And here we'll just show that I want these two together. And then we've got this part right here, but I'm going to reverse the sign with a minus sign in front. We've got the 2 factored out, so this becomes 1 over n plus 1 minus 1 over n plus c over 2. But then notice that what we have for each of these sums, this is going to match our series definition that we have over here for the Digamma function. Just rearranging it, we have the Euler-Mascheroni constant over here. If I just add it on both sides, this cancels, and now we've got an expression for this sum. On each of these, the z value, our input on the Digamma function, is going to be this thing right here and this thing right here. So what I can do to rewrite this, we're going to have half, multiply it on everything. This piece right here will be this Euler-Mascheroni constant plus Digamma of the input c, which is c plus 1 over 2. Then we're going to have minus, again, Euler-Mascheroni constant plus our input c over 2, so this is going to be Digamma c over 2. But then notice when you distribute the minus sign, constants are going to cancel out. And so let me just clean it up. So our formula for this is going to be just Digamma c plus 1 over 2 minus Digamma c over 2 all over 2, and that's it. Now, one thing I didn't mention earlier is this is a formula that's come up before dealing with an integral on this channel. The integral that's equivalent to this is going to be just integral from 0 to 1, x to the c minus 1 over 1 plus x dx. The reason this works is if you think of this 1 over 1 plus x, you could look at it as 1 over 1 minus x. Then it's in the basic form for geometric series. The bounds are from 0 to 1, so you know you've got divergence, but you know you have convergence with those bounds. So with geometric series, if you did this xc minus 1 really fast, this thing here becomes the sum minus 1 to the n, x to the n. So what's going to happen when you shuffle this thing around, I know I'm doing it really rough, but you're going to have putting these, you get the same base here, so you end up integrating x to the c plus n minus 1. Well, when you do this integral with power rule, what's going to happen is this becomes just x to the c plus n over c plus n. But when you evaluate the bounds, the 0, 0, the 1's 1, what you're going to get is 1 over c plus n. What I really should do is write it as 1 over n plus c. but this thing is exactly this thing that we started with. So again, this sum is the same thing as this integral right here. And I think it's a really useful formula because with the Digamma function, there's a lot of values we can calculate. There's different formulas we can use to calculate. And then in order to get it into this form, like even if you had like some constant on the end, you could factor it out. You could, if you had, you know, an n+1 or something, you can do index changes. So there's a lot of ways to get it into these forms. You can get into one of these forms and then go to this formula. Okay, so there you go. That's it for today. Thanks everyone for watching. Have a good day.